Okay, hi everyone. So we'll finish what we did start with the Poisson distribution. So Poisson distribution is one of the discrete probability distribution, and we apply this distribution when the events occurs in specific, usually in a specific period of time or area. So specific time, this time could be like a day or a minute or an hour or a year, decade, any period of time. The area could be like a room or a piece of land or a piece of paper. So maybe number of the type or error in a piece of paper or a paper of a page of any book. It will be following that variable will be follow Poisson distribution. Okay, so this Poisson distribution or the formula of this Poisson distribution, it will be this one: probability of x equal mu to the power x e to the power negative mu divided by x factorial, where the random variable x is discrete, so taking accountable values going from 0 to infinity. So we don't have an upper limit for this distribution. Remember when we did binomial distribution, we did say binomial distribution probability of xq is n minus x, and we have x equal to 0, 1, 2 till a specific number n, or we did say n in binomial distribution is fixed, but here n is we don't have a limit upper for the variable x, so it could be any value greater than 1. Remember that e is a constant value equal to this value. So E equal 2.71828, a constant number all the time. And then mu here is the mean of that, is the mean of Poisson distribution, and X is our random variable that we are interested to study. So here, the requirement of Poisson distribution, remember, the random variable is the number of occurrence of that event in some interval. So number of customers coming to the store, it will be following a Poisson distribution, okay? So one very important condition, that occurrence must be random. So now, if we have a clinic and the patient coming, for each patient have an appointment at a specific time, this is not random. So the occurrence must be random. So we can, so the example of the store is the best example. So I open my store at 8 a.m. and I close it at 8 p.m. maybe. And then the number of customers coming to that store randomly, they will be following Poisson distribution. So we cannot say that Chris will come first and then maybe Jean will come second and so on. This is not random. So if those events happening totally at random, then we can say this is Poisson distribution, okay? Which this is here, independent. So we cannot say this is John come first, Chris come second, and so on. And then the occurrence must be uniformly distributed. Let me give you the example here. So I did say I opened my store at 8 and I close it at 8. So this is the probability of occurrence, any event, okay? So let's say any period of time here, let's say from 9 to 10 a.m. And then any other period, maybe from 3 to 4 p.m. So the probability that my event will occur in those two periods of time will be exactly the same, equally likely. They have the same probability, okay? Here, Poisson distribution, we have only one parameter for Poisson distribution. Remember, with binomial, we did say we have two parameters, which is n, the sample size, and b, which is the probability of success. But here, we only have one parameter, which is mu. So we can know the Poisson distribution. What we need to know about Poisson distribution, just the mu. So we can say expected x for this distribution equal mu, or the mean for Poisson distribution equal mu, standard deviation equal to square root of mu, and then from here variance, which is sigma square, equal to mu, which is the only distribution that mean and variance equal to each other. So the only distribution mu or mean equal variance equal mu is the Poisson distribution. This and this is the same. Okay, yes. So we did say that we the Poisson distribution is determined. We can know the Poisson distribution just by knowing the mean of that distribution. Also, we did say we don't have an upper limit for x. So x will take values from 0 to unlimited. We don't have any upper limit for Poisson distribution. So let's see this example. So we have here, we have here 55 years period of time since 1960. There were 336 hurricanes. Okay, so now we have time, and we have some events, which is 336 hurricanes. So those some events occurring at specific period of time. So this is a Poisson distribution, right? So the first, so they said he did assume it's a Poisson distribution, but yes, we can know this is Poisson distribution. Why? Because we have a period of time and we have randomly events occurring in that period of time, which is 336 hurricanes. Then the first, they said, what is a mu? So mu for this one, it will be the number of hurricanes divided by number of years, right? So here we have 336 hurricane and we have 55 years. So we can say that mu equal to 6.1 per year. So we have 6.1 hurricane per year, okay? Good. So this is the first one. So let's go to the next one. So find the probability that in randomly selected year, there were exactly 8. So this is exactly 8 hurricanes. So now the question is probability of X exactly equal to 8 hurricanes, okay? And then we did know that mu equal to 6.1, right? From the first part of the question. So now, so let me write the formula again. Probability of X equal to mu to the power X e to the negative mu divided by X factorial, okay? So now this one, mu, we have it. It's 6.1 to the power X, or let's do it here, down here. So it will be probability of X equal to 8 equal to mu, which is 6.1. It's here, right? To the power 8 E, which is, we got E is a constant number, so we can keep it E. So you can even in your calculator do it like E, or you can put the value of E, which is 2.71828, E to the power negative 6.1, which is a mu, divided by 8 factorial. Okay, so this value, if you do your calculation, you will get this value equal to probability of X equal to 8 equal to 0.107. Okay, so this is the probability here. Or you can, even if you want to do it like maybe you can, if you want to write it like this, is the same, right? B at 8, or X equal to 8, which will equal to 1.07. So now the probability that we have exactly 8 hurricanes in a randomly selected year, it will be 0.107. So let's go to the next one. They said, okay, in this 50 years period, there were exactly 5 years. There were actually 5 years with 8 hurricanes. Okay, how does this actual results compare to the probability found in part B? So let's see. In part B, we got probability of 8, or getting 8 hurricanes in randomly selected year, 0.107. And we have how many? We have 55 years. So 55 years times 0.107 equal to 5.9 years. Okay, so now if we compare this 5.9 year with this 5 years, it will be not really big different between those two values, right? So then we can say that the Poisson distribution appear to be a good model. Okay, so let's go back to this one. I'll show you part B. So I'll show you how to find this value using technology. Okay, so let's go to here, and let's go to stat disk and go to analysis, and then probability distribution, and then all the way down to Poisson distribution. So what we need for this distribution, we only need a mu, and we did know that mu equals 6.1, right? So evaluate, and then we our question was about what? Probability of X equal to 8. So this is X. Go all the way to X equal to 8, and you will find this probability, which is 0.107. Okay, so which is this value here. Okay, so then let's see. So this is the answer for this question. So we did say A, it's a number of hurricanes divided by the number of years. So we got 6.1 hurricane per year. And then this is how to find probability of X equal to 8. Remember, we did say E equal this value, which is 2.7182. And then we can say, okay, the probability of exactly 8 hurricanes in a specific year or in randomly selected year is 0.107. And then for part C, we did say probability of that we have 8 hurricanes in 1 year is 0.17. Multiply this by 55 years, we got 5.9 years. So comparing 5.9 year to 5 years given in the question, so we can say this Poisson distribution appears to work quite well with this data. Okay, and then the next step, we will have Poisson distribution as approximation to binomial distribution. So in some cases, it's easier to use Poisson distribution as an approximation for binomial. What's the requirement for this? We have two requirements. One, n large n or large enough n, big value of n, and then n times probability of success less than or equal to 10. Some books you will find it like this. They put it like this: NB is less than or equal to 10, and also NQ less than or equal to 10. And so, by the way, some of the books they put it as a 5. So this is not strict number, but the idea is if n is large enough, and probability of success is very small, which is close to 0, then we can use Poisson distribution as approximation to binomial distribution. So let's say we did say for Poisson distribution, we need only just one parameter, which is a mu, right? Which is a mu. So we can use a mu of binomial distribution. Remember, when they find mu of binomial distribution equal NB, and sigma equals square root of NBQ. So now, if we want to use a Poisson as approximation of binomial, we can use the mean of binomial distribution, right? So we can use this value as a mean of Poisson distribution. So let's see this example now. So now here we have like to pick like 4 numbers or 4 select sequence of 4 digits, right? So let's do it like this. So we have 4 digits: 1, 2, 3, 4. Okay, and those digits from 0 to 9, and we have only one right code. Just an example, we can consider this is the right code, okay, or the winning code. Okay, so now how many number we can select here in the first place here? We can select any number from 0 to 9, which is 0, 1, 2, 3, 4 up to 9, then 10 numbers here. What about here? It will be again from 0 to 9, and here it will be 0 to 9, and here it will be 0 to 9. So it will be 10 times 10 times 10 times 10, right? It will be like this: 10 times 10 times 10 times 10, which is 10,000 number, right? So imagine that the first digit, it will be, the first combination 0, 0, 0, and then 0, 0, 0, 1, 0, 0, 0, 2, all the way to 9, 9, 9, 9. So then how many combination? 10,000 combination. Okay, good. So, and then what's the probability that I will get the right, the winning code? So probability in this case, here the number of cases, right? The number of trials. And up there, how many correct code we have? Just we have only one correct code, which is this here. So the probability of success B will be 0.001, right? So now here you go. Let's take all this here, and let me write n equal to probability of success equal to 0.001. 0.0001. Okay, what about n now? So in the end, they said, okay, if you play this game once every day, so you will play just only one time every day, find the probability of winning at least one in a year. So if you want to play just one every year, every day, or once every day, then you have to play 365 times, right? So this is the number of times that you will play this game. So now, good. So now let's see here. So now let's see that can we use a Poisson distribution or not? So the requirement is what? N times B equal to N, which is 365 times 0.0001, which is equal to 0.0365. So this value is less than 10, right? And we know that N is greater than 100, right? Those two requirements here. So now, since those two requirements valid, then we can use a Poisson distribution as an approximation to binomial distribution. So let me write the, remember, for binomial distribution, for Poisson distribution, we need a mu, and the mu equal N times B, which is this value, 0.0365. Let me write it up here. So because I have some extra work I want to do, so mu equal to 0.0365. Okay, good. So now let's go back to the question, what they ask us to do. Find the probability of winning at least once a year. So at least once, that's mean what at least once. So maybe we will win just only one time, okay, or two times or three times, or and all the way to an unlimited number of times, which is here it will be 365 days, right? So if we want to find this probability, so we will find all those probability, right? X equal to 2, all the way up to probability of X equal to 365, right? 365. But since we want to do Poisson distribution, we don't care about this value, right? Because we can go up to infinity. So it will be like this all the way. But remember that we have the summation of those probability, I mean the summation of all values, that's probability. So probability of X equal to 0 plus probability. So let me just explain this here. So now at least once, so this here equal probability of X greater than or equal to 1, right? At least once. So that's mean 1 or 2 or 3 and so on. So this is what we are looking for now. But remember, from the summation of probability of X, summation probability of X equal to 1, right? From X equal to 0 to infinity if we want to use Poisson distribution. So okay, so we can write this as probability of X equal to 0 plus probability of X equal to 1 plus probability of X equal to 2 all the way to infinity. So all this summation equal to 1, right? But remember that this part, let me circle it with green, this part and this part is exactly the same, right? So I can write probability of x equal to 0 plus probability of x greater than or equal to 1 equal to 1, right? Which is this value. Just I put this here. Great. So now let's just make some space here. So this will be equal to 1, right? Let me, this one equal to 1. So I want to get this probability, right? So this probability, if we substitute the probability of x equal to 0 from both sides, this will cancel this. So we left with probability of x greater than or equal to 1 equal 1 minus probability of x equal to 0, right? Now I think we are we done. So let's just take this out. And let me write it up here. Probability of x greater than or equal to 1, which is at least 1 equal 1 minus probability of x equal to 0. Again, now we can find this value, right? This value will be equal 1 minus, so let me write the formula here. The formula is what? Mu to the power x e to the negative mu divided by x factorial, right? So we have x equal to 0 and we have a mu equal to this value. So let's go here. A mu, which is 0.365 to the power x, which is 0, e to the negative 0.0365 divided by 0 factorial. Remember, 0 factorial equal to 1, and anything to the power 0 equal to 1. So now we have this value. So it will be 1 minus e to the negative 0.0365. So this is equal 1, 2. So let's go back, find probability of x equal to 0 using technology. Okay, so let's come here. Which is this value, right? So we have, let me do it again. Probability distribution, Poisson distribution, and then we have the value of, let me just double check with the value of a mu. Let's change the value of a mu here. The value of a mu equal to 0.0365. Okay, so now this probability will at x equal to 0 equal to this value, which is 0.964. Okay, equal to 0.9642. Okay, so it will be 1 minus 0.9642. So this value will be equal to, so that's probability here, let me write it here. Probability of x greater than or equal to 1 equal 1 minus 0.9642, which is 0.0358. So can we find this value right away from technology? So let's go back here. So we did say what? X greater than or equal to 1. So let's go at 1 here. And we go here. The last one, x is greater than or equal to 1. So this is the value we are looking for. Okay. So if you look here to the top here, it will be probability x or greater than, which is what we have. What we have, x greater than or equal to 1. So this is the value. We can find it right away here using technology. Okay. So let's see here. So let's see the answer, check the answer. So this is a mu. And then we did find the probability at x equal to 0. And then just this is the value of probability of x greater than or equal to 1. So let's come here and check this question. Now, if we have this, we have probability, or sorry, B equal to 0.00011, okay? And we have N equal to 9652 children. So, okay. So for this one, it's clear, right? It's clear. Clear B is very small. So let's find B. So here, N is larger than 100, and then B very small. So let's see, N times B equal to 9652 times 0.00011. This value will be equal to 0.106, okay? 106. So now this value is less than 10, right? And also we say that we have N is very large number. So since N is very large, so we have NB is greater than, less than 10, and we have N greater than 100. So we can use Poisson as approximation to normal distribution. Okay, so let me write the value of mu here, which is we do need it. So mu equal NB, right? Mu equal 0.106. Okay, so this is the value of mu. Then the next question, let me come here. The next question, find the probability that the number of tumor cases in a group of 9,652 children is 0 or 1. So remember, now we are looking for probability 0 or 1. Do you remember what this? This is the addition rule, right? We took it in a probability chapter, addition rule. So this one, if you go to addition rule, you will find it. This is equal to probability of 0 plus probability of 1 minus probability of 0 and 1, which is equal to 0, right? Because those two events disjoint. So we did say if we have disjoint events, then the probability of A and B equal to 0. So probability of 0 and 1, so for sure this is equal to 0 because they are disjoint event, or those events never happening at the same time. So now we are looking for those two. Okay, so now if we want to use Poisson distribution, we can easily just apply those. So remember the formula here, probability of X equal to mu to the power X e to the negative mu divided by X factorial. Okay, so using this this one, so we apply twice, one for 0, so just probability of X equal to 0, it will be mu, which is 107 from the part A here, or 106. You can check if it's 6 or 7, I don't know. Okay, to the power X, which is 0, e to the negative 106 divided by 0 factorial plus 0.106 to the power 1 e to the negative 107 point divided by 1 factorial. Remember, 1 factorial and 0 factorial, both of them equal to 1, this value equal to 1, and you can find this probability. So probability of x equal to 0, it will be, let me check here, it will be 0.8, sorry, 8. So probability of x0, it will be 8, I believe 9 plus 0.095. So this will equal to 0.994. Okay, this is the probability. So let's go to technology again here. So let's change mu equal 0.106. Okay, so we need two values, which is those two. This is at 0 and this is at 1. But if you want to get both of them, which is, it will be the answer, our answer that we are looking for, this one, 0.994 or 0.995. This is x. This is, if you look here up there, all the way up, x or fewer. So it will be x less than or equal to 1. Since here, look to this one, this is exactly as a probability of x less than or equal 1. Okay, so remember that Poisson distribution is discrete random variable. So when we say probability of x equal to 0 plus probability of x equal to 1, it's exactly the same as a probability x less than or equal to 1. Also, we can write it exactly the same if probability of x less than 2. So probability of less than 2, because we don't have in between values. So we have 0, 1, 2. X less than 2, that means 0, 1. X equal less than or equal to 1, also it will be the same. Okay, which is, I think we'll see it in C here. So here, remember, probability of x less than or equal to 1 is exactly as the probability of x less than 2. Maybe you'll use it in some example, write it down. Okay, and then the next question, they said here, or C, let's see C first. C, what's the probability that more than 1? More than 1. Okay, more than 1, that means probability x greater than 1, right? More than 1. If they said more than or equal, it will be like this. But they said more than 1, that means x greater than 1. So now we are looking for this value. So x greater than 1, if we want to use the same rule, so it will be x greater than 1, it will be probability. Let me do it here, maybe. Probability of x greater than 1, it will be probability of x equal to 2 plus probability of x equal to 3, and so on to infinity. So this one, we can write it as probability of x greater than or equal to. Remember, because we don't have any values in between, 0, 1, 2. So greater than 1, that's mean we will start from 2. Greater than or equal to 2, also we will start from 2. So now we can see, we can clearly see that's what we are looking for. Now we will go back again to the summation of probability. Summation of probability of x equal to 1. So this summation will start from x equal to 0 to infinity. So let me write it now. This one, I can just plug the values. X equal to 0 plus probability of x equal to 1 plus probability of x equal to 2 plus, and so on, all the way. This is equal to 1, right? So let's maybe just add one more value. So it will be plus probability of x equal to 3 plus, and so on, equal to 1, right? So look to those values here. All those values is basically this, right? So now we can write it as probability of x equal to 0 plus probability of x equal to 1 plus probability of x greater than or equal to 1. But now we are interested in this value. We need this. So we can take those two values to the other side with negative sign. So probability of x greater than or equal to 2 equal to 1 minus probability of x equal to 0 minus probability of x equal to 1. Or just if you want to do it in parentheses like this, it will be plus, since we already have this value. So let's go up here. This value, we already find it since this one here. So this is this value. So now this value is just 0.994. So probability of, let me write it here, probability of x greater than or equal to 2 equal to 1 minus 0.994, which is equal to 0.006. Okay, so now using technology, we can right away find this value if we go and find x or greater than 2. Okay, greater than 2. X. So let's go to technology here and go. This is our example, and see at 2 greater than or equal to 2, which is let me see, just a second. Oh, sorry. Let me go explain something here. Yes. So this is, it will be, if we want to see it at technology, it will be, so remember again, so it will be, look at to this value here, x greater than or equal to 2, it will be probability of, again, it's greater than 1, right? It's exactly the same. So since greater than 1, that's mean we'll start from 2. Greater than or equal to 2, again, we'll start from x equal to 2. And then here, so go to this value, which is, this is x or greater, 0.005, which is, I think, from our using of our approximation values, then the value it will be a little slightly different, but exactly the same value. So if you want to look to this value, which is this is x less than or equal to 1, 0.994, which is this one here, 994, this, because probability of x equals 0 plus probability of x equal to 1, this is equal to probability x less than or equal to 1, right? If you go to the technology and find this value, you will find it equal to 0.994. And the other one, so this one, since we don't use the approximated value, so it will be 0.994, sorry, 99476. So it will be here, 0.99476, I said. Okay, and then when you find 1 minus this value, it should be the value we got, which is over there in the technology. We don't use the approximation value here. It will be this value, which is 0.0052. Last thing, just I want to mention here, when I did this, maybe let me just explain it here. So this value, this value is what? This value is probability. Let me write it here. This value, it will be probability of x less than or equal to 1 plus probability of x greater than or equal to 2 equal to 1. So you can use this one if you like to. I think that's it for this chapter. And let me take a few minutes and then I'll start with the next one.